time to make transforming objects easier and possibly even speed up our rendering process with groups in Chapter 14 of the Ray Tracer Challenge. We start off with a new class called Group, which inherits from our Ray Object class. But unlike the other Ray objects, this one is going to be empty and not provide any kind of geometry. But groups aren't the only containers in town. I make it so that the base class Ray Object contains a parent and child Ray Object so that anything can contain other Ray objects. 3 methods are used: getParent, setParent, and addChild. By the end of this, setParent will do all the work and be used to automatically set the parent variable of the object and also add the child to the parent. I add some tests to make sure objects aren't null and that the object isn't already a child of the parent. I make it so that you never have to add a child to an object by making the method protected. You always just set the parent and everything else happens internally to keep broken hierarchies from happening. The first test just makes sure a group has an empty list of children. The second test makes sure that the child has a parent set to null by default. We'll need to be able to move back and forth between parent and child later. The third test is the real work, making sure objects are added as children. I don't pass at first because I forgot to add an object to the new parent. We need to be able to perform intersections on the group, which should trickle down to the children. We're going to test intersections with a group that's empty, as well as one that contains objects. Right now, we're only caring about objects that are transforming in the group, and not the group transforming itself. But I have a bit of a problem. I didn't follow the book, and my intersection test simply returned the floating point t value of an intersection, and not the object that was intersected along with it. It didn't matter before, since we were testing each object individually. However, now when we perform an intersection test, we'll likely get a list of different objects intersected with. I'm going to spend a few minutes now and refactor my code for this change, which requires fixing methods, variable declarations, and several unit tests. Now we're finished refactoring and can finish this intersection test. It fails because I've yet to actually implement the code for it. The intersection for a group will transform the ray using its inverse matrix, iterate over every child, aggregate all of those child intersections, and then sort them out. At first I forget to do the sorting and that causes some problems. The method that's handling sorting is located in my scene class. Now that intersection handling is really more of a Ray object thing, I first transfer it to the Ray object class, but then I make the wiser decision to move it to the intersection class since Duh, it handles intersections. I also make it static, since I don't really need an instance to invoke the method. I do a little refactoring, and then things work. The pattern class knows nothing about these new parent-child relationships, so the pattern@object method has to be updated to account for moving from world space to object space through a hierarchy. Now the real challenge begins. It's time to implement a boundary system to keep track of the extents of our groups and hopefully reduce render time. The bounds will represent a box that completely encapsulates all of the different objects using a minimum and a maximum point. The book doesn't give you answers for implementing this, just a few bullet points to advise you, so it takes a little while to get everything working. The way I decide to do this is by having every ray object require that it fills in an abstract method called getBounds. This will return the bounds of the object in local space, without any transformations affecting it. I spend a few minutes going through and updating all of my array objects to fulfill this requirement. Here I'm making another method called getBounds, which in my head is going to return the transformed bounds of the object, including the children under it. It will first calculate its own bounds, transforming them into its space, and requesting the bounds of each child object, then transforming each of those into its own space as well. It will then compare the values of the boundary minimum and maximum against the other child objects and determine the smallest and largest. Now, there are some problems here, and I'm going to spend most of the rest of the video fixing it. The book mentions that I need to convert the boundary points into the corners of the cube to properly transform things without getting them cut off. But I don't quite listen, so you're going to see what happens if you ignore the book's advice in this video. I think I'm being clever by adding operations for multiplication to the bounding classes. I'll end up removing these later to keep myself from making this mistake again in the future. The intersection test for bounds is just going to return true or false. I don't need to know where it intersects or normals or any other information. I just need to know whether or not I need to dive further down into this object to the child level and do individual intersections there. The code for the cube is used, with some tweaks to handle the minimum and maximum values that are differing from -1 and +1 of a standard cube. I add an axis enumeration so that I can test against different intersection axes without tripling my code. I'll probably need that somewhere in the future. At the moment, I'm making this bounding box test only happen with groups, but the way I've made it, I could perform it at every single level of the parent-child hierarchy, even without groups. I'll save that if I need to speed things up, especially with the next chapter involving potentially thousands of triangles. Since the book provides no unit test for bounding box checking, I create my own by determining where array would hit the bounding box, or the object, or nothing at all. It's not a perfect test because I omit rotation, and that comes to bite me a bit later on. The first test is just for an object in a group. The next test will be if the object is transformed, and finally if the object and group are transformed. I passed the test. Now to try something the book shows off, rendering lots and lots of spheres. The book boasts that it was able to reduce the number of ray intersection tests by an order of magnitude using bounding boxes. So let's create a crazy complex scene using some loops and check the results. I used the randomization methods I created several videos ago to simplify things. Obviously, I cut out the render time for this video. I don't want to make you sit through it. I tweak things a bit to make it visible and also print out the pixel by pixel progress so I can estimate how long this is going to take. Now I don't do any kind of timing or testing to see if this is actually faster or slower, I'm really just interested in implementing it. It's time for the chapter finale, creation of a hexagon using spheres and cylinders embedded in a group, which are then all embedded in a larger group using transformations. If ever there was a test that things are working, this is it. A corner is made, followed by the edge, and finally the whole thing is assembled using rotations. Well, that would be right if I didn't have giant missing segments. This definitely looks like a problem with the axis-aligned bounding boxes. They seem to be clipping the mesh and stopping intersection tests from being performed. I run the hexagon without the bounding box algorithm and things come out perfectly. So it's definitely my implementation that's the problem. I grasp at nothing and try changing where the ray is transformed, which just makes things worse. The real problem is much deeper than that. I know it has something to do with the rotation of the object, but I'm not sure how yet. I'm not picturing it in my mind. I decide to follow the book's advice and create a method that will convert the minimum and maximum points into the actual 8 corners of the cube. I'm getting closer to the right solution, but I still don't quite see it. The cube's corners are broken into top and bottom, and minimum and maximum values are used to define each of those corners. This method is meant to transform the corners using a matrix object. Each corner is multiplied by the matrix and the entire list is then returned. Each object will take its local bounds and using the matrix convert them into the proper space, and then I'll use each of these individual bounds to then calculate a global bound for everything. Getting the axis-aligned bounding box returns the axis-aligned box after the corners have been transformed. It checks the mins and maxes against all the corners and stores the min and max values. I go through now and apply my axis-aligned bounding box methods to the parent object as well as all the child objects, transforming them and getting their bounding boxes in the correct space. But things aren't going to turn out quite right, as you'll see. I decide to go back and test all of my unit tests since I've made so many changes without checking anything. And there we have it. I fail intersecting the group. It's actually a pretty silly mistake, but takes a good bit of debugging to find. I step through my code numerous times, getting deeper and deeper, and noticing that I'm getting bogus values for my min and max points. They don't appear to be set up properly. Well, it's gotten to the point where I need to take notes as I step further and further into my algorithm, noting where things seem to go right and wrong. Well, there's one of the mistakes, a less than sign instead of a greater than sign when setting the first point. But that's not the bigger mistake. Do you see it? Right there? I make a reference to a point. I'm not setting it as a new point. So when it gets changed, both the min and max get changed because they refer to the same thing. Finally, I see my mistake. I implement a new constructor for points that will copy over the values. Now everything will start working again, at least as far as the unit tests go. Nope, still haven't fixed my bounding box issue. Time to make a new test, and since the cylinder seems to be my problem, I'm going to dive a bit deeper and make sure the bounding box calculations aren't getting messed up. I create a simple cylinder and rotate it, then check my values. I'm trying to see if the bounds truly represent the object. Things appear to work fine. Then I try transforming the object in a group, and that also appears to work. Now I really think it's coming down to the odd rotation of the object, and my bounding box is not capturing that. Once again, trying a stupid transform trick that doesn't work, but I am getting closer. I try to make sense of things by drawing it out, noting where the spheres are in the cylinders, and seeing that it is the back end of the cylinder that keeps getting cut off. I decide I want to try and visualize this by drawing out the bounding boxes. I'm in no mood to spend a ton of time on this, so I decide to copy and paste the rendering method and call it Draw AABBs, where I will check and see if it hit an axis-aligned bounding box. And if I do, I'll draw a white pixel to the screen. Otherwise, it'll just stay black. At least this way I'll get an outline of the overall shape. Well, the entire shape is one big group, so I get one big axis-aligned bounding box. Not exactly what I want, but at least I see that it does encompass the entire object. Now I know it has something to do with the smaller groups around the cylinders and spheres. I decide that rather than using straight white values, I will use a shade of dark gray. I will then combine the existing color in a canvas with it so that I can see layers of bounding boxes. I also remove the outermost group so I can see inside of the cylinder sphere groups. I overlay the output on top of the render, and I can see clearly where the boxes are clipping the cylinders. I'm still not doing something right with those corners. And then it comes to me. I'm not handling the situation properly. I don't want to transform the min and max value, just the local corners. I modify things in my bounds class, removing some of the methods that allow me to transform them in case I forget about this problem in the future. I make it so that I work with the corner points and transform them and then get an axis-aligned bounding box from the object. I now get properly sized axis-aligned bounding boxes around my objects that encompass the entire area. That was a lot of work, but I finally got it functioning. Just goes to show you, you shouldn't give up just because things don't work. Try things out, test them out, and make new ways of understanding them, whether that's drawing a picture or sitting down and doing some math. We've got 2 chapters left: triangles, where I get to import my own meshes as object files, and the last chapter where I get to combine objects into more complicated shapes. I'll see you all next time. So long and goodbye.